Okay, I'm going to extend these parametric equations. I'm going to keep x equal to t squared and y equal to 3t because it's just very convenient to do that. And I'm going to add a z component. Z equals 2 raised to the power t. Okay, so now I can add a column for z. I've got t equal to 0, 1, 2, and 3. We can verify very easily that plugging 0 in here gives us z equals 1. Plugging 3 in gives us z equals 8. And numbers 2 and 4 for t equals 1 and 2. How do we graph that? Well, it's a little inconvenient to actually graph this from the perspective I chose. I would have been better having my x-axis kind of gone this way. But we'll deal with it as it is. Okay, first place, our position vector, and it's a little smudged up here. It says s of t equals t squared I plus 3tj plus 2 raised to the t times k. And it should be obvious what that means. The ti plus t squared I plus 3tj is just the same as what we have here for our position vector. I pointed to the velocity vector, it's position vector. And then the 2 to the t k, k is the unit vector in the z direction. And I'm sure if you understand what I and j are, that you could have conjectured what k is, but that's what it is. So here's our position vector. Now, I didn't clearly delineate which is which. Here's our position vector. Remember, our position vector goes from the origin to whatever point on the curve corresponds to the given value of t. And I did another vector, and I should have used two colors here. But our v of t vector goes from here to here. It might be a little hard to see that. So I'm going to try to fix that just a little bit. I'm going to make this thing purplish red so it can be distinguished in the picture. That t's starting to look like an F. Anyhow, it's a t. Okay, so here's our velocity vector. And our velocity vector doesn't look as long as it did over here, but we can use any scale we want for the velocity vector. There's no inherent relationship between the scale we use for velocity, which is measured in distance units per second, and the scale of our graph, which is measured in just distance units on each axis. We don't have any way of knowing just what a second does to the length of the vector, so the length of the vector could be anything. But then if we do other velocity vectors, they have to be on the same scale as this one. Okay, well, whether you understand that or not, here's our velocity vector. And I'm not going to trace over this in red, but I'll kind of put a red circle around it so we can look at red, red, and red. This should be very easy to understand. Now, how I plotted these points, I'll talk about that in a minute. But if I plotted them reasonably accurately, I've got a reasonably good depiction of this curve. The curve's a little weird around the origin, and I don't have a real good depiction of that because of the angle. I'm looking almost down on the origin along the curve. The velocity vector is just the rate of change of the position vector. No, it's just the derivative of the position vector. Now, we haven't defined the derivative of a vector function, but it's just as intuitive as you would think. We did it over here. We said that the derivative of t squared I plus 3tj was 2ti plus 3j. That's because the derivative of t squared is 2t, and the t squared was times I, so the 2t is times I. And the derivative of 3t is 3, and that's times j, giving us a 3j up here. Same thing here. With the I and the j, it's just the same as it was before. And with the k, we just take the derivative of 2 to the t. And the derivative of 2 to the t is what? It's 2 to the t times the natural log of 2. Now, you might be a little fuzzy on that part of calculus, the derivative of an arbitrary exponential function with an arbitrary base, but, you know, 2 to the t is just e to the t natural log of 2, and you can easily prove that by the laws of logarithms and exponents. And so when you take the derivative, the chain rule gives you this natural log of 2, and you really, as I said in class, need to review the rules for derivatives and chain rules, because derivatives get really hairy in this course and almost always involve chain rules as well as product and quotient rules. Gets very nasty. So you need to be up on taking derivatives. In any case, I haven't proved it, because we're just kind of doing a quick survey and giving you a quick idea where we're going, and then we're going to do it in more detail. But the Pythagorean theorem extends to 3 dimensions. So to get the magnitude of the velocity vector, I just take the square of this component, the square of this component, and the square of this component, add them up, put them under a square root sign, and that's the hypotenuse, which is the magnitude of the velocity. Now I do, as I say, I want to emphasize 2 things. This idea of building up integrals by partitioning intervals, forming Riemann sums. I didn't actually form a Riemann sum, but you need to review that process. Otherwise you won't understand the integrals that arise when we integrate in 2 and 3 dimensions. You want to be able to do derivatives, because one example of a somewhat nasty thing we do, we divide this vector by this magnitude. Okay, that gives us a numerator and a denominator. The denominator is a fairly complicated function. And then we want to take the derivative of that for a reason. Well, this gives you the unit vector as you move along the curve. And if you take the rate at which the unit vector changes, it gives you a normal vector, actually kind of an acceleration vector. And we do that, but we're not going to do that right now. It takes a little while to develop that and to really understand why that works. But we end up having to take the derivative of this thing. This function divided by this. Well, you should be able to take that derivative. And that's one step away from the nastiest derivative we might have to take, which would be the derivative of that derivative. So you really want to have your rules of derivatives firmly in grasp before we go very far at all in this course. They're going to come up very early. Okay, anyhow, there we are. And I hope that gives you some idea of where we might be going and why we want to talk about parametric equations and vector functions.